this video, we are going to look at CAR laws. So first of all, let's start with what C represents, the commutative law. Okay. Most of you must have heard of it, but the word commutative means. So it's the same here also. The order doesn't matter. That's what we say in commutative law. Okay. So you can consider it like this. So if you have A dot B, okay, we can write it down as B dot A. Okay. The order of the signals actually doesn't matter. Okay. You can interchange them as you like. Similarly, you can write down A plus B is equals to B plus A. Okay. I don't think we have to prove this. Obviously, it's going to be the same thing. Why? The expressions actually depend on the gate we are using. Here we are using AND gate, and here we are using OR gate. And in AND gate and OR gate, the order actually doesn't matter. It's also same for the XOR gate. Okay. So if you have A XOR B, you can write it down as B XOR A. Okay. You can write it down as B XOR A. Actually, the order doesn't matter because the gates decide what's the output is. Okay. So, and the gates do not depend on the order of the given signals. Okay. So that's very important. Keep in mind. The next law, the associative law. Okay. In CAR laws, the next one is associative law. Okay. Associative law. Associative law says that you can group signals according to your desire. Okay. So let's say we have something like A plus B plus C. Okay. So let's say we have A plus, let's start from the AND gate. So let's say we have A dot B dot C. Okay. What you can do is you can first of all simplify A dot B. Okay. You can first of all simplify A dot B. Then you can simplify C. Okay. There is no issue with that. Or you can say A dot B dot C. Okay. You can say A dot B dot C. You can simplify B dot C first. Then you can simplify A dot B dot C. Okay. Or since we know commutative law here, we can change the order, right? We can change the order. So we can say A dot C dot B. Okay. So here I'm not only using associative law, I'm also using commutative law. Okay. So this is also possible. Similarly, you can do for A plus B plus C. It's the same for that also. So you can say A plus B plus C, or you can say A plus B plus C, okay, or you can say A plus C, okay, A plus C plus B, okay. So you can simplify the equation in any order. Why am I saying you can simplify A dot B first? Because I'm not just saying a singular signal, okay. I'm not talking about a singular signal that is like A, okay. I'm not talking about a singular signal. A can be a combination of signals, okay. A can be maybe X plus Y. Okay, A can be X plus Y, or it could be anything like X dot Y whole thing bar. Okay, we don't know what it is. Okay, but according to associative law, you can group things like you want. Okay, in any order you want, you can group things. Okay, so keep in mind. And it's the same for XOR also. If you have A XOR, B XOR, C, you can similarly, first of all, simplify A XOR B. Okay. Then you can simplify XOR C, or you can say A XOR B XOR C. Okay, you can simplify those two first, and the rest of it, it's like that. Okay, I don't want to go too deep in this. Okay, it's straightforward. Okay, so these two laws and distributive law, you don't actually have to mention. When you are explaining how you are simplifying in some questions. Okay, we are going to do questions in the next video. They will ask, tell us how you solve the equation. Solve the expressions. Okay, how did you simplify the expression? Then you don't have to specifically mention commutative law, associative law, and distributive law. Okay, so keep that in mind. These three laws, we don't actually have to mention again and again. But other 6 laws, it's better if you mention them. Okay, they expect you to mention them. Okay, so it's not a must to mention commutative law and associative law. Distributive law is also not exactly important because, we normally know that a distributive law is all about expansion. If you have A dot B plus C, you just say A dot B plus A dot C. Okay. So it's just a normal thing. You don't actually have to mention that this is from distributive law. Okay. But if you want to, you can say that. But always keep in mind there is also another distributive law that states A plus B dot A plus C is equals to A plus BC. Okay, A plus B dot C. So this one you have to mention because this cannot be derived directly, right? So you have to mention that. Okay, recaps ahead. Now we are going to talk about the final law. Okay, and a very interesting law actually, the redundancy law. Okay, the redundancy law. The redundancy law. What is redundancy? Well, if something is more than adequate, we call it redundant. Okay, like if it's appearing, you don't need it, but it still appears in different places in different versions. Okay, that's what we call redundant, right? That is what we call redundant. You don't need them actually. So that's what redundancy law states also. Okay, so first of all, redundancy law has two applications. The first one goes like this: A plus A dot B is equals to A. Okay, so this is the first redundant law or redundancy law. How can we derive this? Pretty straightforward. You don't have to think too much. Just do what you know. Okay, in distributive law, you remember, right? A dot in dot B plus C is equals to A plus B. Sorry, A dot B plus B dot C, right? A dot B plus A dot C, right? So if I factorize this, or if I put it in parenthesis, I can go back to this, right? Similarly, that's what we are going to do here. Okay, that's how we are going to derive this instead of using just gates. Okay, so we know we can take the left hand side. Okay, LHS. So LHS is equals to A plus A dot B. Yeah. So if you take A as the common signal, so it will be 1 plus B. Okay, and we know 1 plus B is equals to 1. Why? It's what the identity law suggests. So it will be A dot 1, which is equals to A, again, identity law. Okay, so this is the first application of redundancy law. You don't have to write all these things. You can directly apply this when you're simplifying expressions. Okay, the next one. Okay, the next application of redundancy law, we have A plus A bar B is equals to A plus B. Okay, we have A plus A bar B is equals to A plus B. Well, this is a little bit, confusing to derive because we do a small expansion. Okay, we do a small expansion. So let me teach it to you. Okay, so let me teach it to you. So it comes like this. Okay, so it comes like this. What we have to do is, first of all, let's take the left hand side. We are going to move from left hand side to the right hand side. So let's take the left hand side. The left hand side states that A plus A bar B. Okay, A plus A bar B. So what do we do here? You can't directly simplify anything here. Why? We have A here, we have A bar B here, so we can't do anything. So what we are going to do is, we are going to derive some new signals into this expression. Okay, we are going to put in some new signals into this expression. So what we are going to do is, we are going to say A is equals to, we know A is equals to A dot 1. Why? That's the identity law. So I can say A dot 1 plus A bar B. Okay, and inside A, okay, I can say, instead of 1, I can say it is equals to 1 plus B. Won't you agree with me? Can't I say that? Because we know, okay, I'll erase this and I will write the important things that we are using here. A is equals to A dot 1. And I can say 1 is equals to 1 plus B. Okay, that's what I'm doing here. Okay, so that is done. So here we have A bar B. All right. So once I expand this by applying distributive law, I will get A plus A dot B plus A bar B. Okay, I'm just including A dot B. Okay, and that's the justification for these two steps. Okay, so here what I'm going to do is, I'm going to simplify A dot B plus A bar dot B by taking B out. So it will be A plus B into A plus A bar. Okay, I'm going to say A plus A bar. Okay, so what will be the final answer? Okay, what will be the final answer? So A plus A bar, okay, do you remember the inverse law? A plus A bar is actually equals to 1. That's the inverse law, okay, or complement law. So it will be A plus B into 1. So that is equals to A plus B. So you can see that is equals to right hand side. Okay. you don't have to prove all these things. Okay, you don't have to prove all these things. Okay, so yeah, that's it. And there is also another way to prove this. Okay, I'll teach you that also by applying distributive law directly. Okay, we know a plus b, okay, a plus b dot a plus c is equals to a plus bc. Illaya? You know, a plus b dot a plus c is equals to a plus bc. That's the distributive law. So what we are going to do is we are going to apply this directly to this one. A plus a bar b can be given as, okay, a plus a bar b can be given as a plus a bar, okay, a plus a bar plus, okay, a plus a bar, not plus, dot, okay, a plus b. Okay, what am I doing here? Well, yeah, I'll explain it. Here we have a, so we put a and a here. Okay, similarly here we have a, so I have put a and a here. Okay, here we have b and c, so we have b and c in this order. Similarly, here we have a bar and b, so a bar and b here. Okay, so now you can directly apply this. Why? A plus a bar is equals to 1 according to the inverse law. So 1 into a plus b can be given as a plus b. Okay, a plus b. There are so many things in redundancy law that you can derive by just applying the redundancy law. Okay, so first of all, we have a plus a bar b is equals to a plus b, right? Okay, so what do you think is b plus b bar a? What do you think it is? Well, that is equals to b plus a according to the redundancy law. So can I say that is equals to a plus b by applying the commutative law? I can, right? I can apply commutative law and I can say this is equal to a plus b. So what we can say is a plus a bar b is also equals to b plus b bar a. Okay, a plus a bar b is also equals to b plus b bar a. Okay, so now as I already taught you in De Morgan's law how you can remember things easily, for redundancy law how you can keep things easy is how a plus a bar b. Okay, if you have a signal here and it's inverse with any other signal, okay, then the output will be a plus b, the signal and the any other signal. Okay, well, not and or the any other signal. So you can also consider of it like this: a bar plus ab is equals to a bar plus b. Why? This is the signal, this is the inverse of the signal, and this is the other signal. So the output will be the signal or other signal. Okay, so that's how you have to keep in mind when you're performing simplification of expressions by using redundancy law. So I'm going to stop here, okay, because we have learned about 3I laws, then we learned about 3D laws, and finally we have learned about CAR laws. Okay, trust me, these are very useful, okay, when we are learning about simplification of expressions. So please keep in mind, and we'll do some practice questions in the next video. So yeah, stay tuned.
Thanks for watching the 9th video in our Logic Gate series. If you found this deep dive into the CAR Boolean Laws, Commutative, Associative and Redundancy Law helpful, don't forget to like, share and subscribe for more lessons. Hit the bell icon to stay updated with our latest videos, check out the full playlist to master Logic Gates, and follow us on Instagram. I will see you in the next video. Until then, keep learning and stay curious. Bye bye.